Hello everyone, this is Kenji Fuji from Chiba Institute of Technology speaking. From here, we will begin the lecture of Mechanics of Indeterminate Structures, Chapter 1, Section 1. In this section, I will talk about the internal forces of statically determinate beams. A typical examples of statically determinate beams, simple beams and cantilever beams are often introduced. Here are diagrams of these two statically determinate beams. The one on the left is a simple beam, and the one on the right is a cantilever beam. The points that support a beam are called supports. A simple beam has two supports, while a cantilever beam has one. When various external loads act on a beam, reaction forces occur at the supports, enabling the beam to remain in equilibrium. Here are some examples of statically determinate beams shown in photographs. This is a model of a simple beam. The parts on the left and right act as the supports. A downward load is applied at the midspan of the beam. This is an eave that extends outward from a building. It is an example of a cantilever beam. The point on the right where the beam is fixed to the building serves as a support. The self-weight of the wave produces a downward load on this beam. Here are the conditions for a statically determinate structure. The structure does not move when a vertical load is applied. It does not move when a horizontal load is applied. It does not rotate when an external moment is applied. A structure that satisfies these three conditions and whose support reactions and internal forces can be determined only by using the equations of static equilibrium is called a statically determinate structure. Now, let us explain how to analyze a statically determinate beam. Now, analyzing a statically determinate beam means finding the support reactions and internal forces. First, we assume the reactions at each support. Next, we calculate the reactions using the conditions of static equilibrium. Next, we determine the internal forces at different points along the beam. Finally, we draw the diagrams of these internal forces. This completes the analysis of a statically determinate beam. Next, we will explain the support reactions at each support. First, let us describe the types of supports. Here, we show the three types of support commonly used in statically determinate beam. The one on the left is called a horizontal roller. The one in the middle is called a pinned support. The one on the right is called a fixed end. These differences are summarized as follows. A horizontal roller can move horizontally, but it cannot move vertically. It allows free rotation. A pinned support cannot move either horizontally or vertically, but it allows free rotation. A fixed end cannot move horizontally or vertically, and it does not allow rotation. The number and direction of the support reactions for each type of support are shown here. For the horizontal roller on the left, there is only one reaction, a vertical reaction V. For the pin support in the middle, there are two reactions, a horizontal reaction H and a vertical reaction V. For the fixed end on the right, there are three reactions, a horizontal reaction H, a vertical reaction V, and a moment reaction M. Here is how to calculate the support reactions. The reactions can be obtained by using the following static equilibrium conditions. First, for the horizontal direction, we use sigma x equals 0. This means that the sum of horizontal components of external loads and reactions must be 0. Here, we take the positive direction as to the right. Next, for the vertical direction, we use sigma y equals 0. This means the sum of the vertical components of external loads and reactions must be 0. Here, we take the upward direction as positive. Finally, for moments, we choose any point of the beam and apply sigma m equals 0. This means that the sum of the moments of external loads and reactions about the point must be 0. Here we consider clockwise moment as positive. In simple beams and cantilever beams, there are three unknown reactions. Since we also have three equilibrium equations, we can determine all the unknown reactions from these equations. Let's talk about the internal force that occur in a beam. There are three types of internal forces: axial force, shear force, and bending moment. When these three types of internal forces are illustrated, they appear as shown here. The light orange part represents small portions of the beam, and the red dashed line shows how those portions deform under each type of internal force. First, the axial force is a type of internal force that causes a member to stretch or compress. Next, the shear force is a type of internal force that causes sliding deformation in the member. Finally, the bending moment is a type of internal force that causes the member to bend. In the following sections, we will discuss how to define the sign conventions for each type of internal force. First, let's define the sign convention for axial force. For axial force, tension is defined as positive. An axial force that causes tension is sometimes simply called tensile force. In contrast, compression is defined as negative. An axial force that causes compression is sometimes called compressive force. Next, let's define the sign convention for shear force. A shear force is defined as positive when it acts in a clockwise direction. In contrast, A shear force acting in a counterclockwise direction is defined as negative. Finally, let's define the sign convention for bending moment. A bending moment is defined as positive when the lower side of the beam is in tension. In contrast, a bending moment is defined as negative when the upper side is in tension. Let's explain how to determine internal forces. Internal forces are calculated by cutting the structure and considering the equilibrium between the external loads and the internal forces that appear on the cut section. First, suppose that the reaction to the external loads acting on the beam are already known as shown here. Next, we consider cutting the beam at some point. After cutting the beam, we focus on the left side of the cut, the external load acting on this portion. In this case, the reaction force must be balanced by the internal forces that appear at the cut section by applying the equilibrium equation, horizontal force, vertical force, and moment equilibrium, just as we do when finding reaction forces. We can determine the internal forces. Now, let's talk about internal force diagrams for beams. The rules for drawing these diagrams are as follows. For the axial force diagram, it does not matter whether you choose the upward or downward direction as positive. However, you must always indicate the sign clearly. For the shear force diagram, the same rule applies as for axial force. You must always show the sign. Finally, for the bending moment diagram, the rule is different from the other two. The bending moment diagram must be drawn on the side where tension occurs. In other words, on the concave side of the beam. Note that this is a Japanese convention, and the drawing style may differ in other countries. Here, to help you to visualize the internal forces in a beam, I will show you a photo of a beam model. In this photo, we assume that the left end of the beam is supported by a horizontal roller and the right end is supported by a pin. A weight is placed at the center of the beam, causing it to deflect downward significantly. In this case, the weight at the center acts as the external load. In response to this, the reaction force develops at both supports. At the central part of the beam, tension occurs on the lower side. Here we show the internal force diagrams for this case. Since no axial force occurs, only the shear force diagram and bending moment diagram are shown. Let's first explain the shear force diagram on the left. In the left half of the beam, the upward reaction force creates a positive shear force. Its magnitude is equal to the reaction force at the left support. Then, due to the external load applied at the center of the beam, the right half of the beam has a negative shear force. Its magnitude is equal to the reaction force at the right support. Next, let's look at the bending moment diagram on the right. In this case, the lower side of entire beam is in tension, so the bending moment diagram is drawn on the bottom side of the beam. The bending moment is zero at both ends, and it reaches its maximum value at the point where the external load is applied. Here, please pay attention to the relationship with the shear force. On the right side of the beam, the shear force is positive, and in that region, the bending moment increases downward as we move to the right. In contrast, on the left side of the beam, the shear force is negative, and in that region, the bending moment decreases as we move to the right. As we have seen, this section covers the internal forces of statically determinate beams. The main points of this section are as follows. We first explained two common types of statically determinate beams, the simple beam and the cantilever beam. Next, we explained the procedure for analyzing statically determinate beams. Step 1. Assume the reaction forces at the supports. Step 2. Use the equilibrium equations to determine the reaction forces. Step 3. Calculate the internal forces inside the beam. Step 4. Finally, draw the internal force diagrams. This completes the lecture of Chapter 1, Section 1. Please proceed to Example Problems 1, Section 1.